In the previous module, we derived the general form of the expectation maximization algorithm. In this module, we will consider a few concrete latent variable models and discuss the details how to apply the expectation maximization algorithm to them. So, to start with, let's revisit the Gaussian mixture model and see how the algorithm which we derived from some kind of intuitive considerations fits into this general framework of EM. So, recall that in Gaussian mixture model, we have a data set of points and we want to model them with a mixture of Gaussians, naturally. So, the density of each data point is a weighted sum of several different Gaussian densities. And we have three types of parameters: the weights, the Gaussian locations, and the Gaussian covariance matrices. So on the E step of the expectation maximization algorithm, if we apply it to this Gaussian mixture model, we'll have to find we'll have to assign Q to be the posterior distribution on the latent variable T, given the data and the parameters. It turns out that we did exactly the same thing in the Gaussian mixture model, just from intuitive considerations. So the E step is the same as the first substep of each iteration of GMM, of EM applied to Gaussian mixture model. Okay, so what about the M step? Well, on the M step in the EM algorithm, we have to maximize the expected value of the joint log likelihood with respect to parameters, while fixing Q to be the posterior from the previous iteration. And in the Gaussian mixture model, we decided to use these kind of formulas. So, for example, mean of the first Gaussian will be a weighted average of the data points, with weights being the posterior distributions, or Q in the notation of the EM algorithm, divided by some normalization. So how does these two connect it? Well, let's use the blackboard to derive the connection. So to prove that the maximization of this expected value of logarithm, which EM algorithm asks us to do, is the same as the formulas we kind of intuitively derived for the GMM. So let's look at how can we apply the general form of the expectation maximization algorithm to Gaussian mixture model. So on the M step of the expectation maximization, applied to GMM, so Gaussian mixture model, we would like to maximize the following expression. So we want to maximize the sum with respect to objects, maximize with respect to parameters, by the way, sum with respect to objects in the data set, then expected value with respect to the IV variational distribution, which we found on the E step, of the logarithm of the joint distribution, logarithm of probability or density of xi and ti, given parameters. So let's look closer at this expression in the case of Gaussian mixture model. This thing equals to the sum with respect to objects, again, and then we can rewrite the expected value by the definition. So expected value is just sum with respect to all the values. If we have 3 Gaussians, it will be from 1 to 3, of weights, of probabilities, from the variational distribution Q, times this log joint likelihood. And this logarithm of the joint likelihood actually equals to the xi given ti, which is a Gaussian. So we have some normalization for this Gaussian, times exponent, and let's say that we have one-dimensional data. So in this case we have one-dimensional Gaussian, which looks like this. The xi minus mu c, so the center of the cluster number c, of the Gaussian number c, divided by 2 times the variance of the Gaussian number c. And times the prior, times the probability of ti equals to c, which is pi c. It's also a parameter which we want to optimize for. And so let's write this expression even more. This will be, again, sum with respect to objects, sum with respect to the values of a latent variable, the weights, times the logarithm of pi c divided by z minus the logarithm of exponent of minus something, which is just this something. So it's xi minus mu c. Oh, I'm sorry, I forgot the squared here. The squared divided by 2 times the variance. And let's optimize this expression, for example, with respect to mu1. So the gradient of this whole function with respect to mu1 will be. So first of all, it's sum with respect to objects, as always. So we can push the gradient inside this sum. Then we'll have sum with respect to the Gaussians. But note that the only Gaussian that depends on mu1 is the first one. So all terms corresponding to c equals 2 or c equals 3 will have zero gradient with respect to mu1. So we don't have any summation with respect to c here. Instead, we assume that ti equals to 1. Because otherwise the gradient will be 0 and we don't care. Times gradient of this expression with respect to mu1, which is 0, because pi c doesn't depend on mu1, and the normalization constant of the normal distribution, of the Gaussian distribution, also doesn't depend on the location, on the mean value. So this would be 0 minus, well, here we have this expression. So first of all, we'll have the same normalization. So it's a constant with respect to mu1. And then times the gradient of this expression, which is 2 times xi minus mu c and times minus 1. So gradient of basically the chain rule. And we want to set this gradient to 0 to find the optimal value of mu1. So this 2 and 2 vanish. We can basically divide by 2 in numerator and denominator. And finally, we can multiply this whole expression by what should be mu1 here and sigma 1, because we assume that c is 1. So we can multiply this whole expression by the variance of the first Gaussian, which we actually don't know, but since it's not 0, we can multiply by it, and so it will vanish. And this way we'll have finally the following expression. So this gradient equals to this gradient multiplied by sigma 1 squared equals to the sum of the objects, the weights. The first term here will be minus xi, so it will be like minus xi. Oh, minus times minus gives plus, so it will be plus xi. And minus the second term, sum with respect to objects, the weights. So we're basically decomposing these two terms into two separate expressions, times mu1. And this thing equals to 0. So you can note that here mu1 doesn't depend on I, so we can put brackets here, like this. And finally, it's a linear expression with respect to mu1. So we can write down that mu1 equals to large ratio. So this term, sum with respect to objects, weights, and xi's, divided by some normalization, basically sum with respect to all objects of all the weights. This is the expression for mu1, and you can obviously obtain the same expression for mu2 and mu3. And actually you can also obtain a similar expression for sigma c, for example, by doing the same thing, differentiating with respect to sigma c and setting this gradient to 0. This will be sum with respect to the dataset of xi minus mu c, which we have just computed, divided by squared times the weights, of course, divided by normalization, so divided by the sum of all weights. And also you can solve this maximization problem for pi, so for the prior weights pi. It's a little bit more trickier because you have to take into consideration the constraint. So you have to make sure that pi c is non-negative and that they all sum up to 1. So it makes a proper prior distribution. So pi 1 plus pi 2 plus pi 3 equals to 1. And it's a little bit tricky to take this constraint into consideration when you're maximizing, but you can do that and you will get the following expression. So pi c is basically just the fraction of the points that were assigned to the Gaussian number c. And since our assignments are soft, we'll have just the fraction of the weights assigned to it. So sum of all weights corresponding to the Gaussian number c divided by the normalization, which is just the number of objects. And so you can see here that the formulas for then you apply the general form of the expectation maximization algorithm to Gaussian mixture model. It's basically coincide with what we got, then we applied some intuitive considerations to derive this kind of formulas. So to summarize, the expectation maximization algorithm applied to Gaussian mixture model, if you use the general form of the expectation maximization, gives you exactly the same formulas as we have derived in the first module by just, trying to do something reasonable. So in this case, we proved that this kind of intuitive way of thinking about Gaussian mixture model is just a special case of the EM algorithm. So in the next video, we'll apply EM to some other problems.